Okay, thank you. I'd like to thank the organizer for inviting me to give this presentation. I'll be talking about the possibility of observing collectivity in electron-ion collision. Olga already introduced the topic. I'll try to go in bit details and focus on only on the collectivity. So in heavy ion collision, we are now understanding the properties of hot QCD matter. So this conjecture QCD phase diagram shows us different phases of QCD matter at different temperature and baryonic chemical potential. At low temperature, we have a hadronic phase. At high temperature, we have a quark gluon plasma phase. And the collective flow measurement tell us about the properties of the medium formed in heavy ion collision. That is why it is one of the most interesting observable. So in this talk, I will present what is the present understanding regarding the collective flow and initial condition in heavy ion collision. And I will talk about what is the importance of EIC in understanding the origin of collectivity. Mainly, I will focus on probing the color glass condensate, known as CGC, and also the search for ridge structure in small system. So if we look at this cartoon, it shows different phases after a heavy ion collision. So initially, we have an initial state, and then there's a reconfined phase of quarks and gluons, known as quark gluon plasma. Since the system is expanding, the temperature will cool down, and there will be hadronization, and there will be a hadronic phase where the hadron can interact among themselves, and will finally detect at the detector after the final freeze out. So whatever the observable we measure here depends on the initial condition. So our understanding about the initial condition should be very good. So if we compare similar steps in electron-ion collision, specifically high multiplicity electron-ion collision, so you will have an initial state. It could be CGC or something else, we do not know. And since it's a high multiplicity event, so before the detection, there could be a hadronic rescattering. So the observed collective flow may be depend on both initial state and hadronic rescattering. Okay, so over almost 30 years before, Olitrot presented that anisotropy could be a signature of collective flow in heavy ion collision. So this anisotropy is most commonly used in heavy ion collision to search for collectivity. It was predicted that a large collective flow is considered as a evidence for formation of quark gluon plasma. As you can see, this paper was cited by almost 1,500 times. So if we look at how to measure the collectivity. So this cartoon shows the transverse plane of colliding nuclei at non-zero impact parameter. And as soon as they collide, the new particle that produce, they interact, and interaction will give rise to pressure. And there is an anisotropy in the overlap region. Therefore, the pressure gradient is not same in all directions. Pressure gradient is more along the impact parameter direction compared to the perpendicular to the impact parameter direction. So this pressure gradient transforms the initial anisotropy into momentum anisotropy, and we can measure the collectivity by measuring anisotropy in the momentum space. So here is the first measurement from the relativistic heavy ion collider in gold-gold collision at center of mass energy 130 GeV, where the V2 is plotted as a function of a scaled multiplicity. Black symbols are the data points, where these open bars are the hydrodynamics model calculation, and you can see there a nice agreement for the central collision. And I'd like to point out here that this hydro calculation was done for ideal hydro considering viscosity 0 and smooth initial condition, which is you can see here the energy density distribution in the transverse plane. But in principle, in reality, the nucleon position actually fluctuate event by event in the nucleus. So when the two nuclei collide, we'll get a distribution like this. So in addition to the E2, we'll also have the third order and fourth order eccentricity. And similarly, in the momentum space, we will get the V2, V3, and V4. So to generate the higher harmonic, mainly the odd higher harmonic, we need to include the event by event fluctuation in the initial condition. So what are the commonly used initial conditions? So one of the most commonly used the MC-Glover model. In MC-Glover model, we treat the nucleons as uncorrelated and they are randomly distributed in the transverse plane. And the interaction probability between the two nucleons depends on the two factors. One is relative distance between the two nuclei and the measured nucleon elastic cross section. This plot shows that energy density distribution in the transverse plane, and you can see the effect of fluctuation that included in the model. So this is about the MC-Glover. We also have a couple of two models that is based on CGC model. So one is MC-KLN, one is the IP-Glasma. So what is CGC? So it was predicted that at high energies, the gluon emission and gluon recombination can balance each other and we can reach a dynamical equilibrium of gluon density. So this phase is called the color glass condensate phase or the CGC. So these two models based on the CGC, in IP-Glasma we have CGC plus additional color fluctuation in the subnucleonic scale. As you can compare this, we have a finer fluctuation in the finer scale compared to the MC-KLN in IP-Glasma. Now the azimuthal anisotropy can be used to probe or to understand the initial state in heavy ion collision. This plot shows the eccentricity calculated as a function of impact parameter using the CGC and Glover initial condition. And you can see if we use the CGC MC-KLN model, it gives you a higher eccentricity. Similarly, if you use the hydro plus CGC plus hydro and compare with CGC plus Glover plus hydro, you will get more flow in CGC based model. So this azimuthal anisotropy is found to be very sensitive to the initial state. Now, not only initial state, it has been found that it is also sensitive to the transport properties. This plot shows the V2 as a function of transverse momentum from the hydrodynamical model calculation with CGC initial condition by varying different transport properties like viscosity. Eta by S is the viscosity over entropy density, it's a dimensionless quantity. So if you increase the eta by S, you can see the V2 is decreasing. That is because of viscosity is the dissipative effect and that's reduced the electric flow. So if we compare our experimental measurement, we will be able to estimate what is the viscosity of quark gluon plasma that produced in heavy ion collision. So here is a comparison. This plot shows V2 as a function of transverse momentum. These blacks are the RIC data and these three lines are the hydrodynamical model calculation where Glover initial condition is used, and you can see the data can be explained if we take eta by S is 0.08. Now if we change the initial condition, if you use the scale and CGC model, we will see we need more viscosity, the eta by S is equal to 0.16 to describe the same data. So extracted eta by S depends on choice of initial condition. Therefore, we need to have a good understanding of initial condition. So again, here is the V2 and V3 as a function of number of participants. So the V2 can be well explained by Glover and CGC by varying different eta by S, but if you look at the V3, then CGC model is largely under predict the measured data. Now if you look at another initial condition is IP-Glasma. So IP-Glasma is based on the impact parameter dependent saturation model. It's used event by event geometrical fluctuation for nuclear position. In addition, it used the intrinsic subnucleic scale fluctuation for colored charge. And if you compare here the data and the model prediction, you can see starting from V1 to V5, all can be explained by taking the eta by S equal to 0.12, or if you take the eta by S is temperature dependent. So this is very nice, but is it the end of story? But it is not. If we look at the collectivity in small system, we get a new challenge. So this plot shows measurement of V2 and V3 in a small system like helium gold, D gold, and P gold. So, and this data experimental measurement has been compared with 3 different models. So this red model is called the IP plasma plus hydro. And then we have this blue point, which is a supersonic model, and then this pink is a sonic model. So what is the difference between these 3 models? So IP plasma is a CGC based model, and IP plasma, if you see, it's over predict the V2 values in the all system, but it's nicely explain the V3 values in the all system. Now, if you take the sonic model, which use initial state as a Glover initial Glover model, it explains the V2. You can see the pink line, but it largely under predict the V3 measurement. Now, another version of sonic model is called the supersonic, which use additional pre-flow phase. It explains the V3. You can see the blue, but it starts to over predicting the V2 measurement. So you can see that all the available model cannot simultaneously explain the V2 and V3 in small system. That means we need to have deeper understanding of hadron structure at high energy, and this can be, the EIC can be useful in this regard. So now how to probe this hadron structure at high energy? Or I can say, what is the nature of the dense gluonic matter that we expect at high energy? So this pattern density inside the nuclei cannot be calculated using the perturbative QCD, but we can study its variation by some external probe, is known as virtual photon. So to study the CGC, we need to achieve this gluon saturation scale, and the gluon saturation scale actually depends on this factor, where A is a mass number, X is the Bjorken scale, X. So A is a mass number. So this tells us that if you do the electron-ion collision compared to electron-proton collision, this gluon saturation scale can be reached at very lower energy compared to electron-proton scattering. So here the Q square versus X plot is shown. If you see for particular these values of Q square, you need to go 10 to the minus 5x if you do the electron-proton collision, but same Q square can be achieved in much higher X or lower energy in electron gold nucleus. This is one of the motivation for doing the electron-ion collision at EIC. Now, what is the observable that are sensitive to CGC-like phenomena? One of the observable is the exclusive vector meson production. So here's a Feynman diagram shows a virtual photon from electron fluctuate in QQ bar pair, and it interact with the gluon field of ion, and it create a vector meson like J psi, phi, or rho. And if you measure the cross section of this vector meson production in both electron-ion and electron-proton collision, and if you compare with 2 different type of model, which is shown here, so y-axis is the ratio of the cross section for the electron gold to electron proton. And if you look at on the red data point here, this is a model prediction where no CGC or gluon saturation is included. So this ratio is more than 1 here. Now if you include the saturation physics in the model, you see the large suppression of the phi meson production in EA collision compared to the EP. So this is one of the observable which is very sensitive to the gluon saturation physics. Similarly, J psi you also see the suppression, but the suppression level is not that strong compared to the phi. So to this type of study, we need a detector which can detect all the particle in that event with a high precision and at PID. So there are another observable which is also sensitive, is called dihadron correlation, or it's a back-to-back jet correlation. So here also the photon from the electron interact with the gluon field and create 2 back-to-back jets. And if we measure the back-to-back jet correlation, so we will get a high peak in delta phi equal to pi. And again here we show a model prediction with 2 different model. One in no saturation physics and another is a saturation physics is there. So you can see if we include the gluon saturation, there's a large suppression of back-to-back hadrons correlation. So this could be another good observable to study the saturation physics. And to do this measurement, we need a tracking detector with full azimuth, and wide rapidity coverage is also preferable. Okay, so now moving to the second topic is searching the ridge in small system. If we do a two-particle angular correlation, and this correlation can come from three factors mainly. One is the momentum conservation, that is back-to-back jet. This will give you correlation at delta phi equal to phi. So this plot shows the correlation in delta phi and delta eta. So momentum conservation gives you correlation in delta phi equal to pi over the all the delta eta range. So this is mainly because of the momentum conservation. There is another is local charge conservation within the single jet that gives you delta phi small and delta eta is also small. So this a narrow peak at delta eta equal to 0 and delta phi equal to 0 is mainly from local charge conservation. And also the collectivity can gives you a long range correlation. So this long range pseudo rapidity correlation we observe here is called the ridge, and it's actually signature of collectivity. The question is that can we observe this ridge in electron-ion collision at EIC? Let's look at the data existing. It's already shown by Olga. So this ridge in P-lead and PP collision has been studied at LHC. This is measurement by the CMS experiment. So this first two plot is from P-lead and bottom two plots for PP collision. Left side is the low multiplicity event, the N-track less than 35. And we do not see any ridge-like structure in this low multiplicity P-lead and PP. If we go to the high multiplicity where N-track greater than 110, we do see a ridge-like structure like lead-lead collision in P-lead as well as in PP. So this is for PP and P-lead. What about electron-proton collision? So here is a recent measurement from the H1 collaboration and JUICE collaboration. They have looked at this two-particle angular correlation for different multiplicity bin. So this is for low multiplicity 2 to 4, this is 15 to 20, and this is 15 to 30. And again here also we do not see the clear ridge structure. It will be more clear if you take the projection here in given delta eta window. So in delta phi, when delta phi is very small, we do not see any enhancement or associated yield after background subtraction. So no near side long range correlation we observe in EP, but keep in mind here the measurement has been done for multiplicity less than 50. We do not know if we do this similar measurement in higher multiplicity region. Now this is for EP. What about E plus E minus? So E plus E minus we consider is a very simple system and we understand it very well. But recent measurement shows that if we do a high multiplicity E plus E minus collision, there is a signature of enhancement or ridge-like structure in the long range near side delta phi. So this one is for inclusive and this one high multiplicity, multiplicity greater than 50. So if you take the projection for a given delta eta, left side for inclusive, you can see data and Monte Carlo is consistent. However, if you high multiplicity, we see the data is, there's an enhancement compared to the Monte Carlo reference level. And if you integrate the enhanced associated yield and compare with the multiplicity, we get this measurement from E plus E minus collision. And it's also within the error bar consistent with the measurement from PP collision done by Alice. So this is very interesting, is also challenging to understand what is the origin of collectivity. So LF's collaboration also studied the Fourier coefficient from the two-particle angular correlation. The left side plot is the V2, V1 and V3. And here you compare the data and Monte Carlo. So this plot is for inclusive event and we do not see any difference for data and Monte Carlo. However, for the high multiplicity, we do see that magnitude of V2 and V3 is larger than the Monte Carlo prediction. This is also giving you hints of collectivity. Now question is, can we observe collectivity in electron-ion collision? So as I said, that high multiplicity event is very interesting to, and EIC will take the data in high multiplicity as a high luminosity is 10 to the power 33 to 34 centimeters square per second. So we can have a high multiplicity event, which will give us opportunity to study the collective behavior. So far the CGC based model predict that significant V2 in electron-ion collision. So this plot shows the V2 as a function of normalized virtuality. So these are the measured prediction for this V2 or in EA collision, and you can see this V2 could be comparable to the V2 you observe in proton-led collision. And we can also study the system size dependence of V2 by varying the virtuality of the virtual photon. Now this brings me to summary. So as I discussed, the azimuthal anisotropy is very interesting, and it's provides insight into both initial condition and transport properties of the medium. And so far the models available that viscous hydrodynamics with eta by s of the order of 0.1, and that incorporate subnuclear fluctuation can explain the data in heavy ion, or the V2, V3, etc. But the existing model failed to explain the V2, V3 and higher harmonic simultaneously. And we observed the sign of collectivity in high multiplicity PP, even E plus E minus collision. And so we're hoping the EIC will play a crucial role in understanding the origin of collectivity. So that's all. Thank you for your attention.
Thank you. Other questions?
I think there is L guys.
Oh, there's one. Okay, sorry.
Yes, thank you for the nice talk. I have two, if I may. Can we go back to this where you say in E plus E minus we see collectivity, something different to what was expected?
Here. So
yeah. What is the systematic error on this data?
I think this error included both statistical and systematic, and
okay.
They integrated the enhanced yield here, and this is the error bar, total error bar, and this gray points at the measurement for PP, and within error bar they are consistent.
Okay.
Other these are the confidence level.
Yeah. So now coming to the EIC. So in heavy ions and probably also in E plus E minus, you can define your production planes where you kind of calculate your V2 in a certain way. In DIS, that is different. Yes. So I think this is something which needs to be understood, whether what is called this V2, what people talk about DIS has anything in common with the V2, which is shown here in heavy ions. From what I remember from the papers, it's not exactly, it's not at all the same. The other thing is also you showed the HERA data, which had a multiplicity of 30.
Yeah.
So in EIC, we will have a multiplicity of maybe 8 on average in the event. So getting 30 is already high, and going higher will be very challenging. So it would be very interesting. It's just not produced because the W is not so much that you can produce so many particles. So it would be very interesting from theory to understand what multiplicity one would need actually to see something.
I agree. Yeah. So I'd like to see that this two particle correlation could be affected by the non-flow. So one should look at the higher order, 4 particle cumulant to study the flow.
Yeah,
so,
exactly. Yeah. And really understand how you have to define your planes, because you have the scattered we always define everything to the virtual photon, and that might be very wrong in doing it in DIS like this.
Any other questions? No? Okay, let's thank our speaker again.
Thank you.